This is Laiho Flores, and this lecture is the beauty of the coupled water energy and carbon cycles. And in many ways, this is sort of a set of lectures that is a final culmination for our semester in Water in the West. And it's really something that fascinates and intrigues and really inspires me. And so I'm very excited to share this set of lectures with you. So here are the learning outcomes for this set of about 5 short lectures. At the end of these lectures, you should be able to list the fluxes of water, energy, and carbon entering and leaving the terrestrial system. You should be able to write a budget equation for the water, energy, and carbon cycles that accounts for those fluxes that you listed. You should be able to identify the flux in these budget equations that links all of these budget equations for the water, energy, and carbon cycles. And then finally, you should be able to reflect on what might limit this particular flux in different parts of the Earth with a specific emphasis on the Western United States. So here is the roadmap for this set of lectures. What we're going to do in the subsequent 3 lectures is we're going to take a conceptual idealized land system. We're going to draw a box around it and create a system, and then we're going to write the storage and flux terms for each, the water, energy, and carbon cycles. And when we account for these fluxes, what we're going to do is for each of these cycles, we're going to write the budget equation that balances the influxes and outfluxes for water, energy, and carbon, and we'll go through each of those. So there's one video each for the water cycle, the energy cycle, and the carbon cycle. And then we're going to collect all of these 3 budget equations together, and we're going to identify the key flux that really links all of these budget equations. And we're going to sort of think about what that means for the global Earth system and particularly in the context of things like climate change. So, but as a quick aside, what I would like to give you a heads up about is that for those of you that haven't taken calculus yet, we're going to be using a slightly more formal definition for our change in storage terms. And so in previous classes, when we wrote budget equations, like for the water budget and the energy budget, we talked about a change in storage, but we're going to be a little bit more mathematically formal in this set of lectures. And specifically what we're going to do is we're going to talk in terms of the derivative of storage, right? And so the derivative is expressed like this fraction here, and really this d stands for change, right? It stands for an infinitesimal change. So here we're talking about the change in storage, right? And in the denominator here, we are talking about an infinitesimal change in time, right? So we read this derivative as the change in storage with respect to time. Okay, and it has a very specific and important meaning that will be important to think about. And so the way that we interpret these derivatives are as the slope of the line tangent to this function s here, the storage, at a specific time. Right? And so you may remember that when you first learned about slopes, right, you learned to compute a slope as the rise over the run. And that's just exactly what this is here, right? So the change in storage is the rise, right? It's like a delta y. And this part that's with respect to time is the run, right? So this is almost like a delta x, right? So this slope of the line, this is basically sort of a slightly more mathematically formal way of expressing something that you have an intuitive understanding of already, which is this idea of a slope, right? So we interpret this ds dt as the slope of the line tangent to this function s, this storage function, at a specific point in time. Okay, so to give you an idea, to come back to this example that we have been using throughout class, this idea that a budget equation can be, you can think of this as balancing an account, right? And so frequently what we talked about in class was this idea that the change in storage or the change in balance of your bank account was just equal to the difference between how much came in and how much went out, right? And so if we go back to this definition here, this is just the slope of the line. This is the rate of change of money in your bank account at a specific point in time, right? So you could, for instance, take an individual day and say, how much money did I have coming in today? How much did I spend? And if I take the difference of these, then that represents the rate of change of my account with respect to time, right? So if my spending is way bigger than my income, this number will be negative and large, meaning that my bank account is quickly decreasing in size, right? The slope is negative and my bank account is going down at a rapid rate, okay? So as we go through these three budget equations for water, energy, and carbon, feel free to come back to this lecture, to come back to this example if it's not quite clear what is meant when we're doing things like talking about the change in storage, the change in water storage with respect to time. Okay, see you in the next lecture.